Hello everybody, welcome back to Radicals. We're going to do something a little different today. I'm going to go ahead and walk you completely through a review assignment. Since you haven't seen some of this material for weeks, I thought it might be a good idea to kind of talk you through the stuff that I talked about back when we were in the middle of Chapter 5. As you remember, Chapter 5 we got interrupted by the stay-at-home order. So we just have a couple sections one section that we had to cover, and now I want to review again. We need to test you on this because we are going to move on to Chapter 6, which kind of takes advantage. We need to take advantage of this material to do that chapter. So that test is going to be Wednesday, May the 6th at 6:55 p.m. as usual. And the review today we're going to be on page 278, and I'm going to start with number 35 to 75. Again, if you have a question about any of these, you can email me at any time, or just rewind and watch it again. I'm going to go over some stuff that probably is more than what's on the homework here, but you can go ahead. This is going to be a pretty long video, so we're going to go through problems. You may have to fast forward through things if you don't need to listen to some of it. All right, let's take a look at the first problem, number 35. All right, let's take a look at some of these at the beginning. They're not too rough. Notice on this problem, it's asked us to simplify, and if there's a perfect square factor in here, we want to be able to take it out to simplify. Also, this plus or minus is actually requesting both answers. If it didn't have the plus or the minus here, it would just be asking for the positive answer. The positive would be implied. Now, this reminds us that we probably should go back and review all the perfect squares, at least up for a while here. I'm going to do that real quick here. The perfect squares are 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 25, 36, 49, 64, 81. You need to do this and do it fairly quickly so you know how to do these. This is 144 then, 169. Now this is 13 squared here, so things are going to start getting a little harder here. You might want to review these again. 14 squared is 196. 15 squared is 225. 16 squared. Go ahead and go back through this list. You should have them in your notes somewhere. And 16 is 256. So lo and behold, we found one here. You need to know all these. I'm going to go a little bit farther here. 289. 18 is 324, 19 is 361, and 20 is 400. So these are the perfect squares up to 20 times 20. You need to know these. So in a minute we'll talk about the perfect cubes as well. So square root of 256 is 16, plus or minus 16. All right, let's take a look at the next one. All right, let's take a look at this one. This is asking for the cube root of something. Now, because we just got done talking about negative square roots, one of the common errors that people make is think that, oh, I has got to be involved here. No, I is not involved here. I is a function of square roots, not of cube roots. You can actually take the cube root of a negative. For example, the cube root of negative 8 would be negative 2 times negative 2 times negative 2, or it's negative 2, isn't it? So you can take the cube root, an odd root of a negative number. Even roots, they'd have to be positive. But odd roots, like 3, 5, 7, and so forth, you can take the root of a negative. So here's one where we kind of need to maybe go through those perfect cubes. Let's make a list here again. This is probably a good idea to go through this list again. Perfect cubes. Well, 1 cubed is 1. And of course, if 1 cubed is 1, a negative 1, if 1 cubed is 1, then a negative 1 cubed is a negative 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. Yeah, 64. 4 times 4 is 16 times 4. 5 cubed is 125. 6 cubed, I think it's 216. Let's find out here. 6 times 6 is 36, times another 6. Yeah, that's 216. So the cube root of 216 is going to be 6. But we want the cube root of a negative 216. So the answer here is going to have to be a negative 6. A negative 6. Negative 6 times negative 6 times negative 6. 3 negatives give me a negative 216. So just remember that negatives under the radical are okay and don't involve I if it's an odd index up there. Let's look at the next one. All right, let's take a look at this problem here. Notice that a square and a square root undo each other. So the answer here ought to be a negative 8. It ought to be a negative 8. And some of you might say, well, don't we square this first and get 64? And the square root of 64 is 8. Well, that's true, except if you recall, when we start out with an even power and we end up with an odd exponent, we have to put absolute value around something. So the truth of the matter is here it's really hard for people to know what to do on this problem, but the correct answer here is actually 8, because it's the absolute value of negative 8, if you recall. So some people might think that this other one is supposed to be true, but because we have that absolute value, it started out with an even exponent and ended up with an odd exponent, there's a 1 here, then that means that we should put absolute value on it. So the correct answer there is actually 8. All right, let's take a look at this one. This is asking for the 5th root of something. Well, if you recall, powers of powers tells us that when we raise something to a power, we would multiply the exponents, but when we actually take a root of a power, we divide the exponents. So what can I multiply times together 5 times to get c to the 5th? Well, it'd have to be c. So simply divide the exponents here. 5 divided by 5 is c to the 1st, and 15 divided by 5 is 3. So this is d to the 3rd. So c to the 1st, d to the 3rd. Remember, you're dividing the exponents when you take a root of something. Number 39, square root of x to the 4th minus 3, quantity squared. And once again, a square and a square root undo each other. So this is actually x to the 4th minus 3. However, the exponent started out even and ended up odd. Right here, see it's odd, you don't see it, but there's an odd here. Started out even and ended up odd. That means our answer has to have absolute value on it. Okay? Just bear in mind that's an easy mistake for people to make. Number 40, the cube root of 512 plus x squared raised to the 3rd power. And once again, a cube and a cube root undo each other. So we get 512 plus x squared. The cube and the cube root undo each other. Now there's no absolute value on this because it didn't start out even and end up odd. Okay, it didn't start out even. It started out odd and ended odd. So we don't need absolute value on that problem. Number 41, the 4th root of 16 m to the 8th. All right, so we're going to be taking this, the 4th root of 16 and the 4th root of m to the 8th. Well, let's do m to the 8th first because I can just divide the exponents here. So it's going to be m squared. 4 goes into 8. M squared 4 times would give me m to the 8th. And what's the 4th root of 16? Well, let's see. 2 times 2 is 4, times 2 is 8, times 2 is 16. Yeah, it happens to be 2. The 4th root of 16 is 2. So your answer is just 2 times m squared. All right, let's take a look at this one. Here's a problem where, because of the square root here, there's this somehow belief that you could actually take the square root of a squared and just get a, and then whatever this is. But the reality is because this is a trinomial, you can't just take the root of each part. You can take the root of each part if these were products. But again, these are addends. And just as we've done before, you can't cancel addends in fractions. You can't take the square root of addends either. But what I noticed looking at this, and this is sort of the eyesight that you develop, is this happens to be a perfect trinomial square. And I recognize that it factors to a minus 5, and another a minus 5. That would be negative 5a, another negative 5a, there's negative 10. There it is. Well, this is actually something that can be written as a minus 5 squared. All right, now we can take the square root of this. So the square root of something squared happens to be just the base, and that's what we have here. Once again, it started out even and ended up odd, so I need absolute value on this problem. Okay? If you need some help on that absolute value idea, go back in your book to that section 5.5 and see if you can figure out again how that works. It's described in there. All right, let's move on to the next section. That was section 5.5. Now we're going to move on to section 5.6. I'm just going to take these one at a time. All right, let's take a look at number 43. And you're asked to simplify. And that means that you put it in simplest, let's write this out, simplest radical form. Simplest radical form. Now let's review what that means, simplest radical form. This is found on page 260, if you want to flip back there. There are some requirements for simplest radical form. The first requirement is that it has no negative exponents. We don't have a problem with that here. Number 2, it has no fractional exponents. Actually, hang on a second. It has no fractional exponents in the denominator. Well, we're not dealing with fractional exponents yet in the denominator. It is not a complex fraction. A complex fraction is a fraction where there's a fraction within a fraction, not a complex fraction. A complex fraction would look like this, like 1/5 over 2/3. That's a complex fraction. That's not allowed. And finally, the index, and the index happens to be this number at the top, on the corner. The index has to be the smallest possible. Okay, so let's see if we can do something to simplify this problem. I suspect the only problem we need to do is to get this in simplest radical form. I'm going to have to get the smallest index possible. Also, I can tell there's probably some perfect factors underneath the radical. So the fifth one would be perfect radical, in this case fifth, factors under the radical. No perfect square factors under the radical. Okay, you may need to go back to your notes and take a look at that. Let's try this problem, okay? All right, I look at 128 and I recognize that 128 can be factored. Let's see, that'd be 2 times 64, and 64 is 2 times 32, and 32 is 2 times 16, and 16 is 2 times 2 times 2. Oh, look, 2 to the 6th power is 128. So this is easy. The 6th root of 128 must be equal to 2. The 6th root of 128. You could probably use your calculator to come up with that too. Your calculator, remember, you would end up entering the button I think it's in the math menu. Enter the button 6. It would have an N here, I believe, and then it would have an X down here. You enter this button, which I think you got to put the 6 in first. So type in 6, hit that button, and then you'd hit, in this case, 128, and that should come up with 2 for your answer. If you're going to use your calculator, that's okay on the test here. All right, let's take a look at this one. Now, we can't add these together. If we were multiplying, this would be the square root of 100, but we're not multiplying. In order to add them, they have to have like radicals, and I'll show you what that means here in a second again. Also, I noticed that 20 has a perfect square factor under it. It's 4. So this is 4 times 5. So we're going to take out the 4 and we're going to leave the 5 behind. Okay, so the square root of 5 just comes down. And the square root of 4 is 2 times the square root of 5. So the square root of 20 is equal to 2 root 5. Now they have like radicals. They both square root of 5. So I can add them together. Remember, there's a 1 up front here. So this is 3 root 5. 3 root 5. All right, now if you can't really do these with your calculator because the problems are asking for answers in simplest radical form. So you have to develop the smell to smell a perfect square factor. And I see that there's a 4 in here. So let's break this up into 4 times 3. And I see that there's a 25 in here. If you get perfect square factors, then you're going to break them apart here. If they don't have a perfect square factor, there's nothing you can do about it. Well, the square root of 4 is 2. So 5 times that 2 is 10, root 3. And then over here, the square root of 25 is 5. So this is 3 times 5, or 15, root 3. All right? Take the 5 out of there, take a 2 out of there. Now, both of these are like radicals, so I can take one away from the other. They both have the square root of 3. It's a like radical. 10 minus 15 is a negative 5 root 3. All right, let's take a look at 46. It looks really complicated, but it really isn't. These are like radicals. They're the fifth root of 11. Just like in the last problem we had the square root of 3. The fifth root of 11, they're both like radicals. So we can simply add them together. The coefficients out front, 6 minus 8 is a negative 2, fifth root of 11. And of course 11, there's nothing we can do with that. Number 47, square root of 8 plus the square root of 12 squared. Now, since I recognize that the square root of 12 actually has a perfect square factor in it, and so does 8, let's simplify that first. That might make our problem easier. This is the square root of 4 times 2, and this is the square root of 4 times 3. Okay, well then I recognize this has to be 2 root 2 plus 2 root 3 quantity squared. Okay? Now that means we're going to square this binomial here. We can't just square each part and call it good. We have to actually FOIL this thing. So this is going to be 2 root 2 plus 2 root 3 times itself. 2 root 2 plus 2 root 3. I might run out of room here, but we'll see how far we can get on this, okay? It's this binomial squared. All right, we're going to FOIL. Now remember, you multiply the numbers out front and you multiply the radicals together. So here we go. I'm first. 2 times 2 is 4, and root 2 times root 2 is root 4. I'll come back and clean that up later. Outer, 2 times 2 is 4. Root 2 times root 3 is root 6. Inner, 2 times 2 is 4. Root 3 times root 2 is another root 6. Those two are identical, which we kind of expect. And the last one, 2 times 2 is 4, and root 3 times root 3 is root 9. Okay, we're going to clean this up a little bit. We're just going to do it in one more step here. The square root of 4 is 2. So this is 4 times 2, or 8. These are like radicals and can be added together. 8 root 6. And this is, the square root of 9 is 3, so 4 times 3 is 12. So here's my final answer, except I need to add the 8 and the 12 together. I'm out of room here, so let's put it up here. 8 and 12 is 20, plus 8 root 6. There would be your final answer. 20 plus 8 root 6. Again, remember, you can add like radicals. Okay. It was easier probably to simplify this like we did at the beginning. If you were trying to work with these big numbers, it would have been a little bit more work for you. Next one. All right, let's take a look at number 48. I recognize that this has actually got a perfect square factor. So this is 4 times 2. And this one is not a perfect square factor, but you know what I'm going to do is I'm going to break it up into two factors anyway and see if that doesn't help us a little. Remember, the square root of a number can be broken up into the product of two factors. Okay, and I'm going to do the same thing here. I'm going to call this the square root of 3 times the square root of 7. Now the reason I did that is I recognize that these two are going to be easy to multiply together and take the square root of. So that's why I did it. I noticed that I can actually get a 3 out of both of these, and that would allow me to actually multiply those together. So what do we got here? Well, this is 2 root 2 times root 9 times, and I'm going to multiply these back together, root 35. I got the 9 by multiplying these two together. So this is root 9 is 3, so 2 times 2, root 2 times 3 times root 35. And so I can multiply the numbers out front together. This is 6 root 35. 2 times 35 is 70. And there's no perfect square factors in 70. So that ought to be my answer here. 6 root 70. 3 times 2 is 6. Root 35 times root 2. There was no 2 in here, so I knew that I didn't have to worry about multiplying those back together. All right, one of the principles or properties of working with radicals is if I have two radicals in a fraction, I can actually put them back together. This is like the square root of 243 over 3. And I could break it apart if I wanted to. I could go either way here if I wanted to. In this problem, it makes sense to go this way and to turn it into this. And I know that because when I divide 3 into 243, it gets to be 81. 243 divided by 3 is 81. And the square root of 81 is 9. So my answer is 9 here. If you did this with your calculator, you'd see the same thing. Here I didn't need to use the calculator to do that. All right, here's that problem where we have a radical in the denominator. And if you recall, we're not allowed to leave radicals in the denominator. And so we're going to do what we call rationalize the denominator. Okay? Denominator. And that means we're going to get this so the number on the bottom does not have an irrational number. Square root of 5 is an irrational number. Now if you recall, what we have to do here is we can't just multiply by the square root of 5. If I did that, I would end up with this going away, but then this one wouldn't go away. And I'd get 3 root 5. That won't work. So if you recall, what we have to do here is we have to multiply by the conjugate. The conjugate. And the conjugate, top and bottom here, would be 3 minus root 5. 3 minus root 5 over 3 minus root 5. So I'm really multiplying by just 1 here. This is just 1. And so I'm just going to change the way this looks in order to get this radical out of the denominator. On the top, nothing happens up there. But on the bottom, I'm going to FOIL this. 3 times 3 is 9. Outside 3 times a negative root 5 or negative 3 root 5. And then the inside terms would be a positive 3 root 5. And then the last term would be negative root 25. Negative times positive is negative root 25. So on the top, that doesn't change. On the bottom, these went out. And that's what we were hoping for. Remember, that those middle terms disappear. In fact, I didn't even need to check those. Remember, if I know that this is a conjugate, those middle terms are going to go out. And of course, this is just negative 5. All right? So 9 minus 5 is 4. My answer should be 3 minus root 5 all over 4. Now the denominator is rationalized, and I'm all done. All right, here's another one. Pretty much like the last one. We have a little something extra on the top here. The problem's pretty much the same. So we're going to multiply both top and bottom here by the conjugate. Okay? On the top, I'm going to have to distribute this in. And on the bottom, we know the middle terms will go out. So let's distribute this in. I end up with 4 root 10 minus root 20. Remember, the number out front gets multiplied times the number out front, and the radical gets multiplied times the radical. So I distribute it in. I have two terms, 4 root 10 and then a negative root 20. I'm going to come back and simplify root 20 in a minute. There's a perfect square factor in there. Now in the denominator, because these are conjugates, we know the middle terms are going to go out. So I'm not even going to bother multiplying O and I. I'm just going to multiply first and last here. So 4 times 4 is 16. And root 2 times a negative root 2 is a negative root 4. Okay, root 2 times negative root 2 is a negative root 4. I didn't even bother to worry about the middle terms. All right, this on the top here is, let's see, that's 4 times 5. And on the bottom, the square root of 4 is 2, so 16 minus 2 would be 14. This, I can still reduce this a little bit here. So I got 4 root 10 minus 2 root 5 all over 14. Now that would be an okay answer. And it might appear on a test question, but in reality it's not in the simplest form. Why? Well, that's because I can pull a 2 out of the top, and I could pull a 2 out of the bottom and reduce it. So I'm just going to reduce all of these by 2. 2 goes in there, 2 root 10. 2 goes in there, 1 root 5 all over 7. So there's your answer. If I could take something out of both terms on the top and all the terms on the bottom, I should be able to reduce it. So there's your answer. Now, this is just the problems in your review. You may need to go back and try some more problems out of the chapter just as a bit of a review. Let's go on to section 5.7. All right, this is a section 5-7 called radical exponents. And what it's saying is we're going to be dealing with fractions as exponents. There's some rules we got to remember here. First of all, a negative exponent forces us to put the thing in the denominator. Put the base in the denominator. Also, these numerators are powers, and the denominators are indexes of radicals. So what I've really got here is the cube root of 27 squared. Or I'd rather write it this way. The cube root of 27 squared. And there's nothing on the top, so I'm going to put a 1 here. Now let's see how everything got here. Well, the 27 moved to the bottom. The cube root is this number on the bottom. That's an index, a root index. Okay? And the number on the top is a power. So everything had meaning here. The negative made it move to the bottom. 2 was a power. 3 was a root. Now, I could have written it this way instead. I could have written it the 27th, the cube root of 27 squared. But that would mean I'd have to square 27 and then take the cube root of it. It's a lot easier just to take the cube root of 27, which I know is 3, and then square that. So this is 1 over 3 squared, and my answer is 1/9 here. Now you could probably have done this with your calculator as long as you use a lot of parentheses here. But this is done completely without the calculator. Correct answer is 1/9. All right. Sometimes things are just easier if you know the rules. Some of you might stick this in the calculator and come up with an answer and how in the world you got it, but it's not that complicated. Remember when you multiply two things together with the same base, you add the exponents. So this is really 9 to the 1/3 plus 5/3. And since these both have the same denominator, this makes it real easy. 9 to the 6/3, which is 9 squared, or just 81. Now, if you know these rules, it's actually going to make your work faster. Since I knew that rule, I wouldn't have to stick that in the calculator. Correct answer is 81 there. Remember, when you're asked to multiply two things with the same base, you add the exponents. Okay, and then I just simplified it. Number 54. All right, here's a problem where we could do a couple of different ways, actually several ways. And I'm going to try to take you down the road that I think is probably the simplest. Now, isn't it true that a negative exponent causes us to put something on the other half of the fraction? So this is really 27 over 8 raised to the positive 2/3. Right? To get rid of that negative exponent, I flip this over. Now I could write each of these similarly. Remember, the bottom number here is a root index, and the top number is a power. So I'm going to write the cube root of 27 squared over the cube root of 8 squared. I could have written it a couple of different ways, but I think that this is the easiest way because I can take the cube root of 27 and the cube root of 8. Well, the cube root of 27 is 3 squared, and the cube root of 8 is 2 squared, so I end up with 9 over 4, 9/4. Correct answer here is 9/4. You could have put the square underneath here, but then you'd have more work to do. Taking the cube root first of both of these was easier. Okay, this was number 54 here. Number 54. All right, here's a problem that tends to give people a little more trouble than it really needs to. We can't leave this denominator with this radical in it. This is a radical. If this exponent is a fraction, if it's not a whole number, if it's a fraction, then it's a radical in the denominator. And I want to get rid of this radical in the denominator. So I'm going to multiply top and bottom by something that will get rid of this radical. Now don't forget that if I'm multiplying, I would add the exponents. So it's going to be y to the something. Well, what can I multiply this by where the exponents added give me a whole number? Well, if I put 3/5 in here, y to the 3/5. 2/5 plus 3/5 gives me 5/5. That's a whole number. And that's what I need, is a whole number exponent in the denominator. So I picked that out because I could see that the fractional exponents had to add up to a whole number. So my answer here is going to be y to the 3/5 over y to the 5/5, which is y to the 3/5 over just y to the 1st. So there's your answer. Now it's expressed where the denominator does not have a rational exponent. It's not an irrational number down there. All right, here's a problem like the last one, but it's actually written in different form here. If I write this in the denominator, it's a radical in the denominator and that's not allowed. If I write this as a fractional exponent, it would be z to the 1/3. Actually makes it easier to solve this problem. Z to the 1/3. So what would I multiply top and bottom by so that this denominator's exponent is a whole number? Well, that's going to have to be z to the 2/3. Z to the 2/3, because 1/3 and 2/3 is 1, and that goes out. So my answer is going to be xy z to the 2/3 all over z to the 3/3, z to the 1, or just z. Now, looks like the original problem is more complicated, or the answer is more complicated than the original problem, but at least we don't have a radical in the denominator here. All right, one more problem in this section. All right, let's take a look at this one. This one's not a lot different than the last one, but I'm going to multiply top and bottom by something that will give me a whole number exponent here. Well, if I multiply this by, say, x to the negative 1/3, I could do that. But you know what? I think I'd rather multiply this times something that will give me a positive number in the denominator for an exponent. Let's call this 5/3. X to the 5/3. Okay? X to the 5/3. That's 5/3 there. Okay? Now why did I pick 5/3? Because 5/3 plus a negative 2/3 is 3/3. It's a whole number. So the denominator is x to the 3/3. Again, remember, you're adding exponents here. 5/3 plus a negative 2/3 gives me 3/3, or the denominator is simply x. So on the top, I got 3x plus 4x squared times x to the 5/3. Okay? Now I notice, before I write it down here, I notice that I can actually pull an x out of both of these terms. And I want to do that because it's going to end up making a difference on the bottom here. Let's take an x out, and I end up with 3 plus 4x times x to the 5/3. I just brought that down. I pulled that x out because I can see that these are going to cancel here now. So if I multiply this in, I will get, I'll get rid of the parentheses. So I'm going to distribute this into both of these. This is 3 times x to the 5/3 plus 4 times x to the 8/3. How did I get 8/3? Well, x, I need to have a common denominator. This is actually 4x to the 3/3, right? 3/3 is the same as 1. So the 3/3 plus the 5/3 gives me 8/3. So there's the answer. Looks a little more complicated, but at least we don't have a radical in the denominator. You may need to study that one again. Look at her again. It was helpful to take out that x to simplify this a little bit. All right, let's go to the next section, which is section 5.8. All right, of all the sections, this one's probably going to give you the least amount of trouble because most everybody's doing real good with this. All right, just let me remind you, however, that anytime you square both sides of an equation, you need to check your answers back in the original. Okay, so we're going to square both sides of this equation to get rid of this radical. Square and a square root undo each other, and I end up with 6 squared is 36. Now if I put that 36 back in the original problem, the square root of 36 is 6. By the way, remember, if there's no sign out in the front, you're just looking for the principal square root, just the principal one. That means the positive one, okay? Number 59. Y to the 1/3 minus 7 equals 0. Okay. Well, what's been done to y? Well, it's been raised to the 1/3 power, and then 7 was subtracted. So we're going to add 7 to both sides, and we get y to the 1/3 equals 7. So how do you undo a power of 1/3? Well, that means the cube root, doesn't it? The 1/3 power, y to the 1/3 means y, the cube root of y. Well, how do you undo the cube rooting? Well, you cube something. So we're going to cube both sides of this equation, and a cube and a cube root undo each other. See, when I multiply the exponents here, powers of powers, it's going to be a 1, and it's going to go out. So y is equal to 7 to the 3rd power, and that would simply be 343. 343. 7 to the 3rd power is 343. All right, let's go ahead and do this one. I want to get x, so I need to undo in the reverse order. What's been done to x? Well, 2's been subtracted, then it was raised to the 3/2 power. Well, how do I undo raising something to the 3/2 power? Well, what I'm going to do is raise both sides to the reciprocal power. The reciprocal of this would be 2/3. So I'm raising both sides to the 2/3 power. 2/3 times 3/2, right? 2/3 times 3/2. They undo each other. A root, these two are multiplied. multiplied together, and I end up with x minus 2 equals negative 8 to the cube root of negative 8, that's what that bottom number means, squared. Or you could just use your calculator and see what you end up with here. But what do we get here? Let's see here. The cube root of a negative 8 is a negative 2. Cube root of a negative 8. Negative 2 times negative 2 times negative 2. And if I square that, remember, there's the power, there's an index, 2 is a power, 3 is an index. Cube root of negative 8 squared. Cube root of a negative 8 is a negative 2. So I get x minus 2 equals negative 2 squared. Well, negative 2 squared is 4. Let's add 2 to both sides, and we find out that x is equal to 6. Now, we did a lot of stuff to this problem, particularly when we squared this negative right here. So it's highly likely that this answer needs to be checked in the original problem. So if I take 6 and stick it back up here in the original problem, 6 minus 2 is 4, and raise that to the 3/2 power. What does that mean? That means the square root of 4 cubed. Square root of 4 cubed. Well, the square root of 4 is 2, and 2 cubed is 8, and that's not equal to negative 8. So this one doesn't work. So in this problem, there's no solution. No solution to this problem. And if the book asks you, or the test asks you for any extraneous answers, you'd have to say 6 was an extraneous answer. It didn't work. But it was one of the answers you came up with. So sometimes I'll ask you not just for the answer, but for any answers that didn't work in the original problem. So this one has no solution, even though 6 came up as an extraneous solution. Next problem. All right, here's problem 61, and just again underscoring from the last problem, it's very important when you square both sides that you always check back in the original problem here the answer you get. All right, let's solve for x. We're going to add 3 to both sides here. Most people won't have too much trouble with this one. And now I'm going to square both sides. This is squared and this is squared, and I end up with the square undoing the square there. The square root and the square undoing each other, and I get 9. Subtracting 5 from both sides, x is equal to 4. Now since I've squared both sides, I need to check that back in the original problem. 4 plus 5 is 9, the square root of 9. Now this is asking for the principal square root, remember. There's no sign out here, so you just have to assume it's positive only. Okay. Square root of 9 is 3, 3 minus 3 is 0. Yes, this one works. Okay. All right, let's go ahead and solve this one. Again, this is probably not too big a problem for most of you. Adding 3 to both sides, we get the square root of 3t minus 5 equals 7. Now we're ready to square both sides. And a square root undo each other. I'll get 49 here. Adding 5 to both sides, 3t is equal to 54. And dividing by 3, t turns out to be 18. 18. So let's stick 18 back in the original problem. Okay? 3 times 18 is 54, minus 5 is 49. Square root of 49 is 7, principal square root. 7 minus 4 is 3. This one's okay. Okay? All right. This is kind of a no-brainer for all of you, I'm sure. We're going to start by squaring both sides, and we get 2x minus 1 equals 9. Square and a square root undid each other there. Adding 1 to both sides, 2x is 10, and x has got to be 5. Stick that back in. 2 times 5 is 10, minus 1 is 9. Square root of 9 is 3. That works. All right, here's a problem with a fourth root of something. Well, this is like saying 2x minus 1 to the fourth power, And either way you do this, it doesn't matter. These two mean the same thing. So if I want to undo taking the fourth root of something, I would raise both of these to the fourth power, either one that you want to do. I'm going to take the first one and just raise it to the fourth power. So I'm going to take the whole thing, raise it to the fourth power. And the fourth root and the fourth power undo each other. So this is 2x minus 1. And 2 to the fourth power. See, 2 times 2 is 4, times 2 is 8, times 2 is 6 is 16. Let's add 1 to both sides. 2x equals 17. And divide by 2. According to this, x is 8.5, 8.5. 8.5, is that right? Yeah, well then I would stick that back in here, and I'm not going to take the time to do that, but this one does work. I know it does because there was no problems with raising any negative numbers to an even power. So I pretty well know that that works. All right, let's go ahead and do this one. This one turns out very easy because there's a single radical on both sides, and if I square both sides, both of these radicals are going to go out. They're just both going to go out, and then I'll just solve this linear equation here. Subtracting y from both sides. And let's add 3 to both sides, and I get 8 equals y. Y is 8. If I stuck that back in the original problem, 8 plus 5 is 13. That's the square root of 13 on the left. Put 8 over here. 2 times 8 is 16. 16 minus 3 is also the square root of 13, so that worked too. So that's okay. One more in this section. All right, let's take a look at this one. You know, one of the things we haven't done anywhere along here is we haven't declared what is not going to be allowed as an answer. And I can see that under the radical here, if I set this equal to 0, y would be a negative 1 if that denominator or that thing under the radical is 0. So y cannot be a negative 1. And similarly over here, y cannot be 4. So let's see what we end up with for answers here, because we may end up discovering that one of these answers isn't going to work, and I can kind of tell by looking underneath the radical here. Now, how do you do these? Well, basically, you try to get one of the radicals alone first, okay? And usually we try to get the simplest one alone first, so it doesn't really matter here. I'm going to move this one that way, so I've got the square root of y plus 1 equals 5 minus the square root of y minus 4. Basically, I subtracted y minus 4 from both sides. Now, at this point, we're going to square both sides. I'm going to square it here, and I got to put parentheses here and square this side. I'm going to end up foiling over here. And this process that we're doing here is going to actually have to be done twice. So we're going to square both sides to get rid of this radical. Well, this is now y plus 1. And over here, if I FOIL this, let me write it out so we can see it. Multiplying it times itself. Well, what do we get? 5 times 5 is 25. 5 times negative root y minus 4, that's a negative 5 root y minus 4. And here's another negative 5 root y minus 4. And now I'm out of room here, but negative root y minus 4 and at times another negative is a positive root y minus 4 squared. Well, what is the square root of something squared? This just becomes y minus 4. So I'm low on room here, so I'm going to move this all over. That's 25. These two add together because they're like radicals. Negative 10 root y minus 4. And this thing here, a square and a square root undo each other, so this is just y minus 4. Let's go ahead and simplify this a little bit here. Let's see if we can get this other radical alone. I'm going to do some simplification here. This is 21. 25 minus 4 minus 10 root y minus 4 plus y. Okay, I just combined those two. Now notice that if I subtracted y from both sides, those would go out. And I'm going to subtract 21 from both sides here and end up with a negative 20 equals negative 10 root y minus 4. Oh, it's simplifying pretty good now. Okay? And if I divide both sides by a negative 10, I will get this radical alone. What do we get? 2. Negative 10 over 20 over negative 10 is 2 root y minus 4. Okay? So we're pretty much out of room here, but I'm going to go ahead and try to continue if I can. If I square both sides, I'll get 4 equals the square and the square root undid each other. And if I add 4 to both sides, I end up with 8. Y is 8. Now that's not one of our excluded values, but I do still want to check it back in the original problem. Here we go, put 8 in here. 8 plus 1 is 9, square root of 9 is 3. Put it at the bottom here. 8 4 is 4, square root of 4 is 2. 3 plus 2 is equal to 5. Yep, that works. Okay? Lots of work here. Too bad I ran out of room, but you have plenty of room on your paper. Now there's one thing we didn't talk about, and that is if a problem is an inequality. So I want to go back and do one of those right now from the previous problems we did. That's an inequality. All right, I'm going to do a special problem that's not on your homework because they didn't talk at all on this homework assignment about doing something that's an inequality. I'm going to go back to problem 63, which is an equation, and I'm going to change this so it's an inequality. This is not one of the problems that you were given, but I'm going to do this just to make sure you understand and remember how to solve an inequality. There's something special we're going to have to do here. All right, you remember that anytime you have an inequality, you need to check. In fact, anytime you have a radical, you're going to have to check to see what that item under the radical cannot be. Well, anything under this radical can't be negative. It can be greater than or equal to 0, but it can't be less than 0. So we're going to set this up and solve this for x to see what the limitations on this domain for x is. Adding 1 to both sides, dividing by 2. We see that in order to make this equation or this inequality valid, x has got to be greater than or equal to 2. This is the domain restriction, if you recall. Okay? Now let's solve this just the way we normally would. We're going to square both sides. We get square and square root undo each other. This is 9. Adding 1 to both sides and dividing by 2. And we get this. Now, the answer says that x is greater than or equal to 5. Well, they both have to be true. This is an and statement. They both have to be true. And so usually what we end up doing is going down and making a graph like this and see what happens. I'm going to put a number over here, 5. And I'm going to put another number here that's at a half. Okay? 1/2. And we're going to check this graph in 3 regions, left, center, and right, to see which ones are true and which aren't true. My guess is the only place that it's true is going to have to be greater than or equal to 5. They both have to be true. So let's check a number in here. Let's check 1. Put 1 in here. 2 times 1 is 2. 2 minus 1 is 1. Square root of 1 is 1. Is 1 greater than or equal to 3? No, 1 is not greater than or equal to 3. This section is a no. Doesn't work. And down here we can see that x has got to be greater than a half, so I'm assuming that this down here would never work. But let's just check 0 in there. Let's check 0. 2 times 0 is 0. 0 minus 1 is a negative 1. Well, we can't take the square root of a negative 1 in the real world. If we had imaginary numbers, we could. But there's no answer here for this. Okay? So we assume that our answer's got to be up here. Let's pick another number, say 6. Okay? 2 times 6 is 12. 12 minus 1 is 11. Well, the square root of 11 is more than 3. The square root of 9 would be 3. So it's about, I don't know, about 3.2. And 3.2 is greater than or equal to 3. So this is a yes. So our final answer here has to be x is greater than or equal to 5. This is our answer because both of these have to be true. So when you do an inequality, make sure that both of them are true. Sometimes it's going to be that this one is going to make a difference. In this problem, it did not make a difference in our answer. But you do need to check your domain restriction before you do the problems. All right, let's go through the last section here. All right, this is a section on complex numbers, which we just went over a couple days ago. This is square root of negative 64 m to the 12th. All right. Well, I want to, since this is the square root, I want to find all the perfect square factors of each of these numbers. And I can see that negative 1 is a perfect square. Remember that the square root of a negative 1 is equal to I. Remember that. And I squared is equal to 1. Okay? So that's a perfect square factor. Square root of this is going to be I. 64 is a perfect square. And m to the 12th is a perfect square because it's got an even exponent here. Everybody's coming out. So the square root of 64 principal is 8. Square root of m to the 12th, divide the exponent. And the square root of a negative 1 is I. So there's your answer. Notice it wasn't asking plus or minus here, so I only need the one answer. Okay? Next one. All right, so this stuff's pretty fresh in your mind, but let's just go through this anyway. These are complex numbers. Real, imaginary. Real, imaginary. I'm going to subtract this second one. This is a complex number, but I'm going to have to distribute the negative in. So let's get rid of the parentheses here. Minus a minus is plus. Minus a positive is negative. There, we've gotten rid of, we're subtracting both of those, and that means we change the signs on them. Now, the real parts get added together. These are real, that's 10. These are imaginary. We add those together and we get negative 10i. Negative 10i. Okay, next problem. All right, let's do this one. Just a reminder that you cannot multiply two negative radicals together. You'll get rid of an I value, which is important here. Negative 9. Well, let's see. That's negative 1 times 9. And this is negative 4. That's negative 1 times 4. I've broken this up into perfect square factors. Remember, negative 1 is a perfect square. Okay? Well, this becomes 3i when I take it out. And this becomes 2i when I take it out. So this is negative 18i times 4i. Negative 18i times 4i. Now when I multiply these together, I get negative 72i squared. Well, don't forget that I squared is really a negative, whoops, it should say a negative 1. I did that yesterday too. That's a negative 1. I squared is a negative 1. So this is negative 72 times a negative 1, or the correct answer here is 72. All right, here's one of those problems where we recognize that we raise this I to higher powers. Remember that we're looking for multiples of 4 that we can break this up into. I don't just want the even exponents. I need to have multiples of 4. I to the 4th times I to the 2nd. That's I to the 6th. And the reason I did that is because multiples of 4i, I to the 4th, is the same as 1. Okay? And I squared is a negative 1 right here. So 1 times a negative 1 is a negative 1. Correct answer there is a negative 1. All right, now we're going to FOIL these two. Treat the I like it's a variable, except when you get I squared, you got to turn it to negative 1. So here we go. FOIL, 3 times 5 is 15. Inner terms would be, or outer terms would be negative 6i. Inner terms is 20i. And last terms would be negative 8i squared. Now this is the one section that people miss on the test. They multiply I times I and they don't come up with I squared. Make sure you have an I squared here. Now we know that I squared is the same as a negative 1. Right here, see? So I squared is equal to a negative 1. So this is actually a negative 8 times a negative 1, or positive 8. So 15 plus a positive 8 is 23. And then add together these two in the middle, they are like terms. That gives me 14i. 23 plus 14i. Make sure you're curling your eyes there. All right, number 72. Did you notice something here in this problem? You did, didn't you? Yeah, this is actually two conjugates. And we know that if we have conjugates that we multiply together, the middle terms will undo each other. They go out. So I'm going to do the problem and not worry about that, and we're going to verify that that's really true. So we're foiling here. Square root of 3 times square root of 6 times square root of 6 is the square root of 36. Outer terms would be square root of 6 times I. Inner terms is the square root of 6 times I. Make sure that I is not under the radical there. And then last terms, I times negative I is a negative I squared. Now notice, let's see. Oh, this one should have been a negative here, I guess. Root 6 times negative I is a negative root 6i. Yeah, that's right. These two are supposed to go out, okay? They do. They undo each other, and I get 6 minus, what's minus a negative 1? I squared is a negative 1. That's plus 1. So 6 plus 1 should give me 7. 6 plus 1 gives me 7. All right. Well, we are going to simplify this. And why is it not simplified? Well, I is a radical. And we can't leave radicals in the denominator. So we're going to multiply top and bottom here by whatever it takes to get rid of this radical. Well, if I multiply by I, that's not going to do it, because when I distribute in, I'll still have an I remaining with this term. I'm going to multiply by the conjugate, top and bottom. So here we go. The numerator, FOIL. 1 times 1 is 1. 1 times I is 1i. 1 times I is another 1i. I times I is I squared. Okay? And on the bottom, we have 1 times 1 is 1. I times 1 is a 1i. And I times negative 1 is a negative I. And negative 1 times I, or a negative I times I is a negative I squared. All right, these two we've got to change because they're I squareds. Okay, so I got 1 plus 2i plus a I squared. Well, that's a negative I, or negative 1. And on the bottom, this happens to be a negative 1, or a positive 1. So 1 plus 1 on the bottom, and these two in the middle went out. See that? They went out. So I end up with 2i, 1 minus 1 is out, over 2, and then simplifying, I just get I for my answer here. I is the answer. Don't forget that I squared is a negative 1, every time. All right, let's do this one. Basically the same idea. We're going to multiply top and bottom by the conjugate of this denominator. And I'm going to FOIL both. We get 4 minus 8i minus 3i plus 6i squared all over 1. And the middle terms will go out here. So I get minus 4i squared. Well, I squared is a negative 1. So this is all equal to a negative 6. True? Negative 1 times 6 is a negative 6. And this is all equal to a positive 4. Isn't that right? Negative 1 times a negative 4 is a positive 4. So I get 4 minus 6 is a negative 2 on the top, minus 11i. All over 4 plus 1 is 5. So this would be your answer. However, your book wants to write it where we're split these up. Let's split this thing up so we got both parts separated. Negative 2/5 minus 11/5 I. That's the way we usually write these, is we split up the real part and the imaginary part. All right, one more. All right, once again, same idea. We're gonna multiply top and bottom here by the conjugate. Here we go. 12 minus 6i minus 36i plus 18i squared. Bottom, 16, middle terms are going out, minus 4i squared. Well, what do we end up with here? Well, this is equal to a negative 18. I squared is a negative 1. And 12. 12 and a negative 18 is a negative 6. I got in the middle terms here, I got negative 42i. And on the bottom, this is a positive 4. Negative 1 times negative 4 is a positive. This is 20. So that would be a correct answer, except I can take a 2 out of the top and the bottom here, and I'm going to get negative 3 minus 21i all over 10. Or if I write this the way we're supposed to, negative 3/10 minus 21/10 I. That's the way we're supposed to write it. All right, let's take a look at the future here, okay? All right, well, your future is we're going to move on to this, get to take this test on Chapter 5B here on radicals. That test is on Wednesday, May the 6th, 6:55 in the evening. Be sure to do the review on page 281. These problems some of them are a little different than the review that I did, so make sure you do these and check your answers. All right? If you have a question, send me an email. I'll set up some time. I can work with you a little bit. Have a good one.